Hi, and welcome to our next session here in our chapter on regularization. So this chapter is on Bayesian priors and how regularized risk minimization can also be seen as maximum a posteriori estimation in Bayes. And there's a strong correspondence, strong equivalence between using Bayesian priors and using certain penalty structures. Especially we'll discuss the correspondence between Gaussian priors and L2 penalties and Laplace priors and L1 penalties. So the whole session is not too long. I would say the derivation and the argument is not very complicated, but understanding this correspondence, I would say, is hugely important to get another theoretical lens on the concept of regularization and to get another theoretical perspective on machine learning in general. And here now specifically tying this in with the Bayesian framework. So we've already discussed the strong connection, I would say equivalence, between maximum likelihood estimation in statistics and empirical risk minimization in machine learning. We'll now generalize this for regularized risk minimization. And for that, I would like you to look at what we have. I would like you to consider here the general form of the Bayes theorem when we talk about priors and posteriors for parameterized distributions. So let's say we have some parameterized distribution here, P of y, given a parameter vector theta that we want to do inference on, and some feature vectors or feature vector x. Okay? And in order to apply the Bayesian framework, we of course also need a prior distribution on theta now, because theta is a random variable. It's not fixed as we usually model it like in the frequentist framework. It's now a random variable. And the Bayesian framework tells us that the posterior distribution here for theta, given now x and y, so posterior distribution of the parameter we are interested in, given the data we have seen, we can write like that, okay? And this term here, we can kind of disregard if we are only interested in optimizing the thing. If we are only interested in figuring out, for example, the point of maximum a posteriori probability, because this doesn't depend on theta, right? So if you want to optimize that to find its maximum, we could simply just consider this thing here, which is the likelihood times the prior. Okay, so the prior, now we have to assume a structure here. This we can measure if we have fixed a certain model class, which means we can now compute the posterior, and this is what we actually want to maximize. And this is in general, this posterior distribution is what we use to do inference, to perform inference in the Bayesian framework. And we have kind of looked at this before. So the whole trick is now looking at everything. It's the same trick as constructing the correspondence for maximum likelihood and empirical risk minimization. We just now look at everything in negative log space. Okay, so before we were maximizing things, now we want to minimize. So we negate the whole thing. More importantly, we go to log space. And this here is the same thing that we considered before when we did the correspondence for maximum likelihood estimation. So this we will simply identify with our loss, which has a single O and not two. And this here we will identify now with our penalty, okay, with our regularizer. If our prior distribution Q, if this is constant, so if we use something like a uniform or a non-informative prior, then the second term would be irrelevant if we optimize for theta, and we would still arrive at empirical risk minimization, and we would have exactly this equivalence between maximum likelihood estimation and ERM in front of us. If we choose an informative prior, then we identify here the minus log of that prior with our penalty structure J. So the log prior, I should probably say the negative log prior, corresponds to our regularizer, and this additional lambda, which we have in regularized risk minimization, which controls the strength of our penalty, then usually influences the peakness of our prior distribution. So this is usually related to the inverse variance and the strength of our prior. And you'll see this very concretely in a few seconds when we consider the Gaussian prior and the Laplacian prior, which I guess we are doing exactly here. So it's fairly easy to see that L2 regularization corresponds to a zero mean Gaussian prior with some constant variance tau squared here, okay? And in order to show this, that this is really easy to see, I'll do that on the next slide, that, I mean, just take negative log of things and you should be able to derive this yourself. You could also do this for the L1, here for the Laplacian. And then if you consider going to negative log space of the Laplacian density, you will immediately see that the only thing that remains is basically an absolute value term. And this is going to correspond then to L1 penalization. And here you can see the form of these priors for Gaussian and for Laplace. You can also see how the peakness changes. If we control here, if we vary our variance parameters of these two prior distributions, and the more we make that peaked around zero, the more we encourage shrinkages of our parameters. The stronger the prior is, the stronger our assumption is for our model, the stronger the constraints are. So these are all kind of equivalent ways of phrasing things. You could also ask, hey, we did consider elastic net before, so this was a combination between L1 and L2. Is there also a corresponding prior distribution? Answer is yes. So this is usually constructed, I guess that is not very surprising, as a compromise between Gaussian and Laplacian priors. Technically, this can become a little bit more complicated. I've left out the details here, but you can look into these two papers, I guess, especially into this one here. Both of these explain this very well, but at the end, it's going to be a mix between a Gaussian and a Laplacian. So I've promised that we can very directly and easily see that what I've claimed before is actually true. So let's now consider the Gaussian prior and show that this is really equivalent to L2 regularization. So I'm now using a Gaussian prior with a zero mean. I'm assuming I have D parameters. I'm using a simple diagonal structure. So each of my parameters has a prior distribution of a uniform normal distribution with a variance of tau squared. And all of them are independent, okay? So everything is uncorrelated. Under Gaussian, I could have also said independent. And yeah, so there's a prior like that for each individual parameter. And the variance of this thing here would be tau squared, okay? Now, what is now my density for my whole parameter vector theta? Well, it is simply the product over all of these univariate zero mean Gaussians with variance tau squared. Okay, I'm just using phi here as a symbol for the distribution, for the density of my Gaussian in 1D. And I can also write down the multivariate formula here for the Gaussian on the right-hand side. And you should recognize that. And now I can write down the formula for my posterior already in negative log space, as we've seen on the slide before. And this thing here, that's just what we're going to identify with our empirical risk later on. But for the second term, this is what we are focusing on here. I'm now simply inserting this formula for the Gaussian prior, and you can see what happens if we take the log of things. What happens then? Well, let me just remove the scribbling again. So this product here is turned into this sum. There is this first term, which take the log of that, but even that doesn't really matter, because in the whole thing, there's not really a theta anymore. So in optimization, we don't even care about that, right? And then for the second term, you see the log canceling out the exp, and then the minus from the minus log cancels out this minus here. So the only thing that remains is this here. Yeah. So this is just squared norm of theta times our control constant here, 1 divided by 2 tau squared. So we can now identify that. We can identify now tau to the minus 2, basically with our lambda. And we have now our regularized risk minimization here. And we can also see that how this inverse variance, how the precision actually controls our shrinkage. Here's a further example. So here I've used just to visualize this even more, I've now used a super simple data generating process, just with one parameter here, theta times some Gaussian noise. And I'm assuming that the true value of theta is 1. I'll now put a Gaussian prior on theta, again with a prior variance of tau squared, and I'll consider 3 different values for tau, so 0.25, 0.5, and 2. I'll sample now a couple of points. I'll analytically construct the posterior distribution of theta, because in this very simple example I can easily do that, and I can also analytically calculate the location of my maximum a posteriori maximizer. Okay? And I've now plotted and visualized my prior densities here on the left hand side. So if tau is 2, I guess that's, let me check that. So yeah, if tau is 2, we have this blue thing here, right? So then we are not, it's not uninformative, but we're getting kind of close to an uninformative prior. And the smaller tau becomes, the larger, in a certain sense, the corresponding lambda becomes. So the more peaked we become around the zero origin, and the more we constrain our model, and the more, prior information, in a certain sense, we assume there to be. Okay, so this here is the smallest tau value I'm considering. So this is 0.25, and I now take the inverse of that to get the correspondence to lambda. So that would correspond to a large lambda value. Because of that, a strong regularization. Yeah, and here you can now see how the posterior distributions look like for these different tau values, and it also shouldn't come that much of a surprise what happens there. So if we have a more uninformative prior, we are more peaked around the 1 here in this case, because the true parameter value is actually theta equals 1, and we can kind of more easily move to that. But for the smaller tau values, where we are more peaked around the 0, we would have to see way more evidence to move away from our prior assumption that the true value is actually located somewhere close to the 0, which it isn't, right? Because it's located at the 1. What you can also see is where I've now also constructed here the corresponding L2 regularized empirical risk minimization problem, and you can see the objectives for these here with the corresponding lambda values, and you can also see where the minimizers of these are located, and you can see that the minimizer location exactly coincides with the MAP location from the Bayesian perspective, which is exactly what, I don't want to say claimed before on the slides, which I've actually derived before on the slides, but this example I guess confirms it, in a simple context. Okay, that ends the session here. See you in the next one.